Hello, everyone. This is Group Delaware, and the fluid system that our group analyzed is the Austera Pearl Reactor 10K. The Pearl reactor was developed in Vancouver, Canada, and has expanded across the US and Europe as of today. The purpose of the Pearl reactor is to manage nutrients by recovering renewable phosphorus and nitrogen to create an eco-friendly fertilizer. The Pearl fits into the main or side stream and operates by removing excess phosphorus from the treatment plant by adding magnesium to control the pH setting, which allows nutrients to crystallize into highly pure fertilizer granules. Here is a diagram of our fluid system. The control volume we chose to apply the principles of fluid mechanics is represented by the red dotted line. Our fluid is sludge originating from the post-digestion feed tank. Our objective is to compute the force the fluid imposes on the pipe bend between the post-digestion feed tank and the reactor. And we will do this by applying 3 fluid mechanics principles. To find the force exerted on the bend, we needed to first compute both the inlet and outlet velocities. So we applied the continuity equation where we solve for the velocity at the inlet and outlet. For the fluid flow assumption, it was assumed that the fluid flow is steady state and the fluid is incompressible fluid. Since the diameters at the inlet and outlet are the same, it was assumed that the areas and velocities are the same at the inlet and outlet, as you can see in the drawing. For the known values, the pipe diameter was 0.445 meters and the weight flow rate was 1.12 meters cubed per second. We applied the continuity equation as follows. We used the known diameters to compute the inlet and outlet areas with the assumption that the inlet and outlet areas and velocities are equal. We rearranged the continuity equation to solve for velocity, which ended up being 7.18 meters per second.
Next, we needed to assess the flow work along the designated control volume. Particularly, we needed to evaluate the outlet pressure and having known the inlet pressure. We did so by applying our second principle, the work energy principle. Now, we chose to apply the Bernoulli equation as opposed to the work energy equation because in our chosen control volume, there is no work done or on or by the system. So in employing the Bernoulli equation, we assume that the pressure forces along the sides of the control surface normal to the flow do 0 work, and therefore we only need to consider the pressure forces at the inlet and the outlet. Other assumptions we made to apply the Bernoulli principle was that the inlet and outlet points lie on the same streamline as in the drawing, that the flow was steady state and inviscid because there is no mixing or turbulence in the drawn control volume, and the fluid was incompressible. We use the known values displayed in the diagram to compute the outlet pressure. We also made the simplifying assumption that the velocity squared over gravitational constant terms were equal on both sides of the equation, since the inlet and outlet velocity were equal. So we eliminated them. Inputting the rest of the values, we computed the pressure at the outlet to be 918 kilopascals. Next, we needed to solve for the X and Z components of the force the fluid imposes on the bend, and ultimately the force itself and the angle at which the force is imposed on the bend. So to do so, we applied our third principle, the impulse momentum theorem. We were able to use this theorem by drawing the assumptions that the flow was steady state and fluid was incompressible. We also made the assumption that the friction along the control volume was negligible, and then the bend we were assessing forms a 90-degree angle. These known values needed to solve for the forces also appear in this diagram of the control volume. As seen here, we're evaluating the angle at which the force is imposed from the negative x-axis, represented by the brown line and theta symbol. And we applied the impulse momentum theorem along the x and z axes as follows. Using the force vectors in the previously shown diagram, we built the respective equations for both component axes. So Please feel free to pause and rewind the video to understand these equations in the context of the diagram. We also separately solve for weight as the specific weight of the fluid times the volume at the bend. And upon inputting the known values, we calculated the x component of the force to be 156 kilonewtons and the z component to be 168 kilonewtons. And lastly, we found the force the fluid imposes on the 90-degree bend and the angle it is imposed on as follows. The force is 229 kilonewtons applied at an angle of 47 degrees from the negative x-axis.
Apart from the force calculation we performed just now, we also brainstormed some ways to improve the overall fluid reactor system. We thought that the efficiency of the reactor should be improved such that the amount of phosphorus it recovers increases so more fertilizer can be made. Although we thought that the weight flow rate through the control volume should be increased to process more fluid at a given time. The reactor should also be redesigned to ensure that the salt index of the fertilizers is 0 so that the plants are safe. Lastly, this technology is relatively new and should be implemented at more wastewater treatment plants. And these are the sources we use to support our assumptions and values. Thank you.